Thank you, Vice Chancellors, our Dean Desnes, and Professor John Rains, and ladies and gentlemen. In this late afternoons, I hope I can illustrate to you a little bit on the materials behavior, its importance in manufacturing and innovations. All right, so as probably usual, I'll probably like to go through a little bit of my background in terms of education and research, and then I'll go to the main topics and looking at some of the examples I've been part of over the years, and some brief comments. But I think probably I should first, because the word innovation is it can mean a lot of things, so I'll probably just first define what we mean by the innovation, at least this afternoon, and it's pretty much process innovations, and it's a definition from a manual from OECD. It refers to implementations of a new or significant improved productions or delivery methods. Right, so that's what I mean by the innovation in this afternoon. Probably let me just go a little bit of my own understanding with my background, and I'll just say the process of innovations is pretty much you start with an innovative idea, new idea, but an idea can come sudden or not sudden, but in my case here, I refer to that idea comes from a gradually or suddenly after many years of research. Right? So this is the idea, and from the idea, and you people try to translate that into development of process. So process development, that can be, according to the definition, this can be incremental, but can be also radical process implementation. Now, if it's successful, the innovation has to be successfully applied. So to apply the process, of course, it has to be a few criteria, but today I won't be using the data to describe that as only infers productivities up, new market, new products, but most importantly, of course, they have to result nowadays. The use of materials, resource, and energy need to be done, and because, as we know, that's quite important in terms of sustainable manufacturing and also sustainable developments. All right, so I'll go to a little bit back to my old day in universities. So I pretty much kind of in the years, and that's my teenage years, and China in the year of that period, some of you may know, some may not know, it's kind of a chaotic years. And as a result of those chaotic, it's two phenomena. One is some of the school, high school, primary school shortens, and then afterwards a lot of young people sent to the countryside, and I was one of those. Sent to it's got to go to a countryside to be a farm laborers, but that's quite common. And with that, I'll probably just mention a little bit. And if you, some of you, if you take some notice in China, now is in the times of power transformation. So the new kind of the group of people, for example, the 7 of those in the standing committee of the standing committee or political proletariat. 7 of those got 4 of those actually got in the old days sent to countryside. So it's quite common. Right. So, and no university. It's university, but you can't go through the normal kind of entrance exam to get to university during that 10 years of turmoil till 77. The higher education's entrance exams were in states, and we called it Gaokao. With that, and 5.7 million people took part, and about 270,000 successful. So it's about 4.7%. So the class of 77s, right, and they started academic year in the following year, 78, and I was just one of those, but also notice, if you also notice and watch China a little bit, in the next few days will be the new premier, and he was also one of the class 77. So this is the historical figure in terms of the start from 77 till now, and you can notice from the red lines there that you can see in the beginning of the 77 is very, very low success rate in terms of you take the exams and go to universities. All right, so that's how I got into the university. So as Vice Chancellor just mentioned, I did my undergraduate in Central South University, and my first couple of years is pretty much the same as mechanical engineering. The only difference is probably a little bit of a chemistry and physical chemistry papers, and the senior years more looking at the materials properties and plastistics and deformation process and associated machinery. So my specialization, my undergraduate, is pretty much shape manufacturing and deformations. And after that, and I left China, and that's also the time I still have doubt in terms of development of China. So I left and I came to New Zealand, and I did, and later on I did my master degrees in building up undergraduate underwater local dry cavity and do the welding with Dr. Gregory. I just seen Dr. Grace come in the room. And with that, it's pretty much a torch, and they figured out where the dry cavity comes from and then the conditions. And after that, of course, I do the associated mechanical property and microstructure analysis and so on. And when I finished, I went on to do a PhD, and I was awarded New Zealand Steel Research Scholarships. And then Dr. Clark, who's not here today, and he pointed me to a project on this particular topic and looking at, right, so most of us would know that zinc on top of steel would protect the steel, but during those years there's a new alloys, and what happened is the interface region is not so clear, so that's what I did my study on, and it turned up to be in the interface a lot of thermodynamic we need to figure out. That's the paper we published part of that, and then later on actually this is one of those compounds that's very important in the interface. And with the coating, then I do a serious characterization, work out the structure and also the growth kinetics, and to understand the thermodynamic and kinetic of the issues. And turned up actually this particular compound is turned up to be very important in my career life. It's actually turned up a few times. Later on you will see. So when I finished, as Vice Chancellor mentioned before, when I finished my PhD, I went to Australia. I joined a company called Pasminco. Pasminco, quite a big international base metal company, and we did always consulting work, short-term work, as well as medium to long-term work for the company and also the international base metal communities. And one of those we did was in one of the area was the coating alloys development, because that is zinc is base metals, and try to work out again the growth kinetic and how that affects the quality of the coatings. And this is some of those we did. But apart from doing short-term consulting and work with the customer, we also, as I mentioned, do short and long-term study, and therefore we also have the opportunity to communicate with the academic and research communities. And also in Pasminco, that is also the time that, if you remember, some of you remember that about 20 years ago, there's a lot of go to your car, you look at those batteries. In the old day, every now and then you had to put water into it. And those are the time that they want to change that to the so-called maintenance-free. With the maintenance-free net acid battery, you need to associate with that, have to do a lot of alloy development. So, and that's the time I spent about 2 or 3 years also. Did a lot of work, castabilities, precipitation hardenings, joining, and corrosion resistance, and so on. I left Pasminco and joined CSIO in 1993, and I spent a few years in Brisbane and Melbourne. And with that, and quite often in CSIO, we do medium to long-term research, but occasionally we also do consulting work as well, because we work with a lot of industrial company, and for example, BPR Automobile and Nissan Castings and Ford Automobile as well. And I spent quite a bit of time on the new process called squeeze casting and semi-solid castings. And to figure out, I think, the melt chemistry under the condition of squeeze castings, what happened, as well as making how the conditions of making good components. And so that's squeeze casting and semi-solid casting in the mid-90s is kind of an emerging manufacturing technology, and that's why CSIO is something new. They quite often jump into it and do a lot of work, and that was one part of that. But every now and then we also need to do work with the existing industry, and that's why we also work with Nissan die castings quite a bit, and these are some of the components over there, and casting component, to a lot of us, you may or may not have heard, but if you just go to your car, you open up your bonnet, and if you just count, it's probably you can count many, mostly are casting now. So it's very important for transportation industry and car industries. And one of the problems I did, I tried to work out those days, is one of that is very much of a headache to the industry called die soldering, and I'll illustrate a little bit more later on these particular topics. And then we try to work it out in terms of under the conditions of die castings. First of all, what's the erosion effect on soldering, and we consider also cavitations, erosion, particle erosions. And then later on, we look at the thermal effect, how that affect the so-called die soldering. And now I'll come back to what is die soldering a little bit later. And we also quantify a lot of the structure as well as the kinetic growth of the so-called soldering layer. I finished CSIO, and I came back in the 2000s to join AUT, and in the 2000s when we first became a university, some of us will remember then, and also the time we try to build up research as well. But the facility in a way is quite primitive in those days. So, and I actually in the first few years also continue to spend some of the times and look at some of the problem. When I was in CSIO, one of those is looking at the thermal issue, how that relate to a certain a mechanism of skin solidifications. And also, again, more of in-depth mechanisms, a study on the die soldering, and as I mentioned earlier. But also at the same times, we also have opened up, I'll try to look for a new topic, and one of the things I did was then a visiting professor. I tried to work with and look at the process of welding of high nitrogen steel, stainless steel. So stainless steel, well, the significance of that is, right, because we all know stainless steel, but a lot of austenitic stainless steel, they are not very strong. For example, if you go to the kitchen, those zinc and those stainless steel, the string of those stainless steel from engineering term, the steel string is probably only about maybe 250. So they are not very strong. So, but in some application, you need very strong austenitic stainless steel. And one of the things is to put nitrogen inside stainless steel for hardening purpose. But when we do the welding, we have a lot of problems. So one of the projects we did is try to figure out why in a specific location we have a lot of gassing, end up with very good pattern of those porosities. And at the same time, I work with Dr. Jules and also Professor Wei Gao from Auckland University, and looking at the mechanisms of local melting and solidification. When you do the welding, here is unmelt, here is a liquid metal somewhere in between. So we try to work out a lot of incipient melting mechanisms, and also the microstructure formations, as well as later on we extend that to look at some of the phases, the dissolution kinetics, and so on. All right, so. And those initial years and the last many years, in some of you may have noticed that I've spent a lot of time doing friction stir welding and processing research. And I'll I'll give a little bit more detail later on, but I'll just list some of the key publications we have done in AUT, and I mean key publication. If we commonly now in academic community, we probably quite often your publication, you look at the impact factor and so on. So what I say key publication are those published in good journal. So published good journal in our field, materials engineering, I think if you get to about impact factor of 2 and upward, they are normal, very good journal. But of course, occasionally some of the high impact, they are not necessarily so good. So we have done quite a bit as well. As later on, I worked with an engineer from Airbus and also quite a few around the world to edit, and the people, of course, they wrote the books. And so this is the kind of academic science what I have done after joining AUT. But at the same time, we also, as engineer, we also work with a number of companies over the years. Here are the list of those industrial R&D consulting work, and also a lot of those student ME work funded by probably a lot of those before by technology in New Zealand. So I give 2 examples here. One is the friction stir thick plate is one we work with Barclay system. Now, of course, they use that for the manufacturing or the backing system for semiconductor device, and quite often they shift their gear overseas, their products overseas. And the other one is I want to mention is one of the ME projects in Robbie. Robbie is not here, and he did this particular one with fractured aluminiums. And this is quite significant, even though it's an ME project, but a lot of industrial relevance. And well, I mentioned that here because Robbie actually went for international conference on aluminium extrusions, and there's a lot of industrial people over there. And one day I received an email all of a sudden, and Robbie said, you know what happened after my representation is that people lined up a long queue trying to talk to him. So it's quite significant. Why? Because there's a lot of industrial people, they do want to understand more and also try to find a way to solve those problematic things. But one of the examples I also like to point it out is the last few years. Daryl Wong is one of those from Trade Enterprise and worked with us with AUT and through the process of introduced the friction stir welding technology up to the 4 patrol vessels for the New Zealand navies. So, right. So I just try to make a point that I think we engineering academics do want to conduct R&D with industries, and what we probably hope for is a more supporting mechanisms that support us to do industrial research in New Zealand. All right, so that's pretty much about myself in terms of from my undergraduate to pretty much now in terms of research. But I just try to point out a little bit from CSIO and also as a research academic in university. So what we do is a lot of research development and occasionally, of course, consulting work as well. And I probably trying to bring up a little bit sometime when we were in CSIO. Quite often we do have some discussion, sometimes it's drive from the top management and talking about the mix of research and how basic research and applied research and how they interrelate to another, and also research how to relate to development works. And sometimes we just so it's dangerous that if you don't do basic or research, or you don't have much to give and for applied research, if you don't do much research, your development work is pretty empty in terms of research from research organizations and so on. So that's I would see that is actually quite important for us that as an engineering research academic, we need to do a whole spectrum of research development and also consulting. And I believe that a proper research, a proper support to this activity would probably have a lot of good benefit in terms of research training, in terms of generating wealth, in terms of protecting our environment. All right, so I'll then look to use a few examples to illustrate the importances of some of the materials behavior in manufacturing method. And the first one is, I go back to look at the interface intermetallic first, right? And again, to look at this one, well, in this particular case, and the idea, and then the incremental developments, and then how they apply. So those within the so-called process innovations. Right, so let's look at zinc first. I borrowed this from international zinc associations. In the time when I was in Pasminco, we also have done quite a bit of work and also interaction with the Net Zinc Research International Research Association. That's a research arm of that association. So I kind of know a little bit about. But this picture here probably it told us quite a bit of story. That zinc, of course, protect a lot of beautiful structure, but of course it protect a lot of other structure as well. From roofing, I think in New Zealand we know and to white goods and car, and also chemical plants, and also now it's probably more popular in terms of looking at those wind power generation. You need to have those, and if you go along the street, of course you see a lot of those power poles, they're galvanized. Right, so, and if I look out from my window, that's what I see, a lot of zinc. So it is very, very important, right? So, and I put in here is a logo from it's from Asians associations of every few years they have conferences. Every continent they have conferences about just zinc, how zinc predict steel. So it's quite important because it's so big of a business. We don't feel, but it is a lot of activity. So what I want to look at now is look in the traditional, if you have a very good zinc coating, the operation is done properly, then you have a very evenly distributed coating thickness. With that, then you have, I'll point it out later on, the so-called intermetallic compounds. And why? Because if you dip a steel or iron into aluminum bars, what happens is the atom of zinc and iron, if after you clean them and all the oxide reduce and come together, and they have then diffuse in, they have interface reactions and nucleation and growth according to the phase diagrams. Now, what is a phase diagram? A phase diagram is it tells us that at what temperature, at what component, what phase you have. Well, that's what it tells us. But on the other hand, it's kind of like a graphical representation of thermodynamic data. You actually can, based on thermodynamic principle, you can predict that. But of course, along the way, you need to have a lot of verification from experimental data. All right, so what happened is for some steel, though, well, it protects steel, but for some steel, it's not so easy that you actually can have an even coating. Why that is the case is, and why it's not even? Because locally, actually can grow very thick, and it become very, very brittle. So it's kind of like a cancer cells over there. It's very dangerous, and I'll illustrate to you. And as a function of the growth and silicon content, and you see it's up and down, and depends on the temperatures. The thermodynamic reasons of that is because once you have the steel, making steel, some of the steel and a lot of steel, actually so-called, during the process that you need to get rid of oxygens, right? And one of the common methods, of course, is use silicon. So silicon kills steel, and afterwards what's left behind is some silicon. And when you have silicon, you have the local, according to thermodynamics, you have a local kind of equilibrium, a liquid silicon and iron. With that, you actually disrupt this kind of a growth. So local, you have liquid coming in. So that's why you have those things. And no, the danger of it, and I can give you one example that it's only about 2 years ago I did a consulting work, and one of the companies said, well, why their galvanized component is keep breaking off, and that is precisely because of similar kind of reasons. Okay, so it turns out, though, the understanding, because of the practical importance of silicon steel reactivity, has been almost a never-ending research topic for a lot of people because of the importance of usage. and I can quantify that as a use-inspired basic research for the last 70 years. Now, solutions or partial solutions actually came quite often before the mechanism are fully understood, and nickel is one of those. So after long time of research, applied research, people figured out what nickel is actually you put it in the milk, it can suppress those funny growths, and that's one of the examples you can see. And of course, from a thermodynamic point of view, people try to explain that it looks though it is a inhibiting ternary layer between the so-called milk and the layer. Right, this inhibiting layer is actually even more so if you look at the so-called continual layer. So this is a process of if all those galvanized sheet goes through those procedures and very fast, very, very fast. And if you look at the zinc bars, and you actually zinc is tied up with about 0.2% aluminium. And it turned out if you have that 0.2% aluminium, during that short dimming time, you don't have intermetallic growth. So end up with a very even, about 20 micron zinc. So it's quite often, it's reasonably deformable. So this is actually turned up to be a very, very good compounds in between. And that is actually because of that is inhibit the normal growth. And I put up this one here is actually you look at the author, Mars, used that diagram to explain the mechanism, why that worked. It's only last year, right? But this is actually the same figures I published 1992, so I feel quite good. Right? So it's actually what happened is in between it because of that ternary, it get the reaction paths go roundabout. Instead of straight line like this, it's go quite round around it. And what happened is because the formations of that aluminium-rich layer, and next to the system is you have aluminium depressions. Because of the aluminium depression, that layer grow very slowly, but thermodynamically it's stable, right? So that is why during the few seconds, that's it. You don't have abnormal growth. Right? So, but of course, there's a lot of equations and growth, and has been considered a lot more theoretical in details. And this is actually, I called it a thermodynamic and kinetics in a good place, and that's for controlling the materials behavior during manufacturing. Okay, I'll turn to another topic here now. Stay with intermetallics, and I'll go back to a little bit in die castings. All right, so a die casting is it's a machine, as I showed you the picture before. You have a machine, but if you look at the machine schematically, it starts with pouring the liquid, and then the piston go forward and inject the liquid to the die, and afterwards it's solidified and open, right? So that's why you have a lot of those casting inside your cars. But the problem is that this process, the gate velocity is just up 40 to 60 meter per second. Right. With that, you will know that with that number, it's very, very high hot aluminium into the die steel. So, and that's why die steel, they don't normally last too long, but they are very costly, and production downtime is even more so. It can cost a lot of money. And one of the problems is called die soldering. It's a failure mode, and it's very costly. It's been intensively studied for decades. And what is soldering? So this is an illustration. If you have a casting, the die cavity is quite complex. So you have a lot of those like fingers, and those liquid comes in here, and afterwards solidify, you take it up, right? But sometimes these two stick together. You don't want them to stick, but they stick together. And that's what is soldering is all about, right? So it's a lot of headache to industries. In this particular case, people bring Fe2Al5. That's the compound, as I mentioned before. It is widely so people should bring that because you don't want joining. And it's a lot in industry. It's a lot of speculation how that happened, right? But it's quite confusing. So the so-called impringements in terms of liquid or the so-called hotspot is a kind of main factor. And in CSIO and in the 90s, we did quite a bit of work and tried to pinpoint what exactly is so important, and that's why I mentioned before those erosion and there's thermal and so on. And we did a lot of work and figured out, actually, it turns out to be the solidification time of the materials at high temperatures. It is the most important factor. And the soldering process, it is a metallurgical, but start with mechanical. So that is a very important issue, mechanical before metallurgical. And we published quite a bit of work and try to illustrate the mechanism of the whole process. However, with that understanding, we thought it's been understood, but even I look at 3 years ago in a very nice modeling work published in a journal, that what they have done is to model the diffusion process of the growth. It's forgotten about the mechanical process, it's forgotten about the nucleation and growth. So it's turned out to be, so it's very nice work, academic work, but essentially it doesn't solve modeling. It doesn't mean it's no value. Later on, somebody pick this up will find it very interesting to inspire other work as well. So, but it does not necessarily model soldering. And you can actually see, and even those books and the guideline published in those associations, they base a lot of those on the so-called aluminizing hot dipping. It's forgotten a lot about the dynamic condition during die casting. You can actually look at a lot of detail. It's a bit like that. And I also have this book is published by Professor John Moore, and some of us would remember John Moore, and that's when I was a PhD student. He was the head of the department in the department in the department. I was doing a PhD. He went on gone back to the U.S., and I later on, of course, find out that he was the head of a department in School of Colorado. And over there, they also have a center of service engineering, and he's a director. And that group has done a lot of work on coating. And one of those they've done is specifically for prevention of soldering. And it's quite interesting, though. You look at those graphs over there, they've done a lot of coding, but they borrow somebody else's graph over there. It's done by somebody's and looking at pretty much dipping mechanisms. And it's totally forgotten the the dynamic of die castings. So, but of course, die soldering as a sequence is very different. And I'll just illustrate. Here is a little bit of a cold and uncold difference in terms of, but to cut the story short, that severe die soldering sequence is for mechanical and then metallurgical. The latter is a aluminizing reaction in solid state, not hot dipping. And it's difficult to be understood in industry. So control is difficult. Costly problem persists. Again and again, after a few years, there were big study again on this. All right, so I turn to still in the topic of intermetallics. I turn to the use of that and of the topic of that relate to welding. Right, so welding, well, we all know, probably most of us know welding, particularly engineer, but it's actually turned out to be very difficult to weld if you have aluminum. The melting point is somewhere around, depends on the alloy, it's about 600, let's say. And then if you have steel or titanium and even copper, you have above 1,000. It's very different in the melting point. It creates a lot of problem if you want to fusion weld them together. Right. The illustration, I don't want to go to the detail why it's a lot of problem, but I can illustrate by this piece of news from Honda that only last year has developed a new technology to weld together steel and aluminum, and now they're in a lot of productions. And with that, they actually use friction stir, right? So it's okay. So let's look at what friction stir, and we did quite a bit of work on friction stir, looking at aluminum and iron, and look at the interface by if I position the tool in different locations, very well controls. So look at the interface development as well as the associated kind of response in terms of property. And you can see actually somewhere if you control well in just touching it, you actually end up with a very high string weld. And in this particular case, I can illustrate that if you pull it, and then this is a so-called tensile testing, you see the difference between that particular weld and the others. In this particular case, what we actually say is we actually need that compound in the interface, but have to well control in a continual layer, not more and no less. And we published this paper, 2013, sorry, only early this year. And one of the review actually in additional comments actually says that optimum toll control has been identified, which remain to be in practice demonstrated as industrial feasible based on the tolerance of this positioning. So it's quite relevant, even though this is additional comments. It's nothing to do with whether we can publish it or not. It's just a discussion. It is very relevant. So with that, I'll conclude this particular topic. And here, I will say that in terms of intermechanics, refer to galvanizing. The behavior is quite complex, not fully understood, but controllable. That's very important. And the process improvement you can make if you can control the behavior. Sometimes you don't understand very well. But die-soldering, on the other hand, is not necessarily so complicated, but people keep ignoring the dynamics of the situation. So therefore, limited success. The problem will always keep going, and we have and have. So even you have a good idea, it's still very hard to translate to industry in this particular case. Welding, right, that's one of those examples. I've mentioned the behaviors now understood, and the process improvement should be made. Even new process can be developed, but will remain to be seen, just for the iron to aluminium. Right, I changed now the topic to look at the semi-solid forming process and look at this process again from the so-called innovative idea. It is innovative idea, the process development and the usage of it. Right, so let's look at the traditional die casting first. Right, so a few years back, we look at in America, the Society of Foundry. They actually put out a paper looking at the last few years, keep changing the traditional iron casting or component to aluminum castings. And with that, the reason for that, of course, because if you analyze the energy usage and actually transportation, it's about 28% with that. And then a lot of those transportation use truck, car, and so on. So if, and the data suggests here, if you have 10% of reduction in weight in a car, you have 6 to 8% improvement in fuel economies, and you have 8% reduction in CO2. So that's why the reason that a car, you want to drive as lighter and lighter and lighter. And that's probably one of the reasons, and a lot of my research has been driven to. I mean, it is, I have done those. So look at a little bit of die casting cycle, die casting liquid, and then finally you have a component. So it starts with transferring melt from a furnace to the die, and then you fill into the die, and then afterwards, with that you have feed flow, and then you have solidifications. And afterwards you open the die and take a casting, start another cycle. Now, but if you're not careful, you look at your casting, inside there, you end up with a lot of porosity. In fact, if you get a component, quite like a casting component in your car, you cut it open, you see, what? How come my car is like this? Right? It is true. I can bet you can find a lot of bigger or smaller. So it has to be what happens. Solidification associated phenomenon in manufacturing often need particular attention, and this is one of the reasons. Okay, so now that's back to some 15 years ago, I was doing some research on squeeze casting and then semi-solid casting. That was the emerging technology. Try to get rid of all those defects in castings. And if you look at semi-solid casting, you look at the casting along the way, you do see very little defect. But also for a long time, people say it is very easy to make. Why is it so easy to make? Because, okay, if you have a semi-solid, if you treat it well as semi-solid, if well-treated alloys and heat it to a certain temperature, what they equate that is kind of like a soft butter. Now, this is 15 or 18 years ago, no, 16, 17 years ago when I was in CSO, and that's what we did. We heat it up, you can actually use a knife, just cut it half, so you can feel it's very easy. So to have a forming process, you have that kind of material, very low, you can feel it in everywhere. It's very good from a manufacturing point of view. And that's what we did. And this is the process of doing, getting for those semi-solid kind of morphology in terms of grains. However, you can see it has to be very well controlled here. The tolerance of the temperatures is only about 2 or 3 degrees. So what happens if you treat it well? The solid spherical in semi-solid state is highly fluid. It's a butterlight in terms of behavior. And this behavior was actually discovered by a PhD student in MIT in the 70s. And he was doing experiments looking at the behavior of during solidification in semi-solid state. And he stirred them out, and he find that if you keep stirring at high speed, you actually, the apparent viscosity it drop all the so-called solid skeleton point, move to a lot higher solid fraction. And that's the base for this particular process, and they realize the significance of that to industry. So they patent it, and that's when the process starts. Okay, so a good idea, they developed the process. Now, for many years, is it successful? Right, so as I mentioned before, because of a lot of, very difficult to control the temperature, that's one thing, and the morphology is another thing. So what happened is it's not so easy. And what happened is how easy it can be deformed. It turned out to be very, very easily. Right, so this is the process you actually can use semi-solid for put in the machine, and afterwards you can have a component. The problem is the control of those materials, and one of the things is very small temperature tolerance. All right, so people, when they are, if some of the group, if they are smart, they can make a lot of good component, high mechanical property, but it's not so easy. I demonstrate by one of the experiments we did when I was in CSIO, and it just by varying the velocity, you can see if you have a little bit high velocities, you have jetting. Low velocity, you can't feel the die. Not like liquid. Liquid is a reasonable tolerance in a way. Semi-solid is not. But actually, if we go back to the one here, looking at why we have that in that particular condition, we can actually borrow a formula developed by Professor Niyama. He's very famous in terms of develop a lot of solidification theories. If you do that, you actually can predict and the solidification layer as a function of solidification time, and you can actually predict by about 1 millimeter, you get to the thickness. It's about the gauge choke, so therefore you can't flow anymore. What happened is, while the gauge speed needs to be very well controlled, but it's difficult to know how and when the casting geometry become more complex. So in reality, in industry, it's not so easy. Only those very smart people can do so. Well, I mean, very educated workforce in a way. Right? So it's interesting, though, if I quote one, Dr. Capranos, he's been in this research in Sheffield University for probably the last 30 years. And he's still doing a little bit, and in the book, I mean, he's published or edited would tell. 2008, he gave a keynote speech, and the title is Semi-Solid Metal Casting, a Process Looking for a Market. After that many years after the process was discovered, I think the title pretty much tells it all. All right, so let's go back to the innovation the process or innovation process. You have a good idea, you can develop the process, but it's important, this is out there in manufacturing, whether you actually can control it. If you don't, good idea will make good idea, process become good process, but you can't use it. Right, so it is a fantastic, well, from my point of view, it is a fantastic process, but whether out there you can actually use it. Okay, the last one is, now I come to friction stir welding and processing is one that, as many of you know, is probably more to my heart in the last few years. And let's look at that process again. Right, so friction stir welding is pretty much very easy. If you join two pieces together, what you need to do is to plunge something like a pin with a solder, like a drilling, right? You put in there, you rotate, you go forward, and that's how it looks, right? So, and that's what in our workshop, and that's how it looks. Nothing fantastic. And what happens is afterwards, you have to join very nicely together. And what happens is this process is a solid state joining process, so no liquid involved. Remember I said before, when you deal with solidification, a lot of problem. Because of that, I think most of us know if you go up to the airplanes, doesn't matter what plane you go, that you go in the first, go in the door, I often look at how many rivets you can see. Because in aircraft, you can't use welding. Because once you weld, well, it's not exactly true. You can still probably, again, some of the smart ones probably can. Because you involve liquid, you come back to solid, in between you generate a lot of defects. But aircraft, you don't want defects, certainly. This is a solid state process. You don't have those solidification associated problems. So, and with that is also the engineering restrictions of using this is quite low. So this is a demonstration. Again, it's Robbie. Robbie's not here when he was in the final years. As a final year student, he tested the temperature and figured out very close to the melting point, but below the melting point. It's basically a solid state. Because of that, so all the so-called 7,000, 2,000 alloy that you see on the aircraft, they're all weldable, right? And this is some of those illustrations or cross sections I put in there that if you don't carefully control it, you actually can generate voids, of course. But as I will illustrate later on, the process is actually really accommodating. And it can weld very thick in one pass, right? In the old day, or even now, if you do fusion welding, you have many parts. This one part depends on your machine. It can come to 0.3 of a millimeter, the so-called micro friction stir welding. Now is finding its way to electronic industry. Right, this is some of those tools we use. Okay, so let's look at little bit of basic principles on that. Well, we know the principle and how it was discovered. It was discovered by a gentleman called Wayne Thomas in 91. Right, so we know traditional fusion welding solidification with relative defect, a lot of problem, but we have to use it. We have to weld, we have to join things together to make structures. Right, laser weldings, high energy beams, well, reduce the degrees of solidification related defects. Friction solid state welding eliminates, but in the old day, friction welding is you can only do linear or rotational, but you can't do that much else. But friction stir, right? So this is a gentleman, Wayne Thomas, and I've been quite fortunate in the last few years. Have various times have some association with him, and he was here 2 years ago, traveling around New Zealand. New Zealand also gave good presentations of in here as well. And Thomas was in the old days, he's a tool maker to start with. He later on worked his way and did an ME, so he gained a lot of knowledge as well. So he worked on a lot of friction-related process, but in his mind, in the very simple motion, how can I use the plasticized materials and somehow transfer and transfer a good mechanism and transfer that for the purpose doing welding? So that has been it was in his mind for a long time. Actually, the story of that discovery has never been actually written. So that's why when I wrote the introductions of that book, I actually communicated with Wayne Thomas, and he said to me, in his mind for a long time, one morning he just all clicked, and that's how he start with using a pole and a pin with a rotating pin with the probe down, and then with that you rotate, plunge in, and the materials and transfer around, and afterwards you can make a good weld. And that's what we know now as a friction stir welding. All right, so okay, good idea. Process development. Look at, is it successful? Right, so only when they apply the process innovations is been successful. So, okay, so let's look at some examples of this friction stir welding that probably I present quite a number of times. It's very easy. If you go online, you can see this example. The very famous example is the fuel tanks in the space shuttles. That, of course, is aluminium. The space tank carries the fuel. You want it as light as possible. So one of the things is aluminium alloys. You put a little bit lithium into it. You increase the strength quite substantially. So therefore, you can reduce a lot of weight. So very beneficial. But you can't weld it very well in using fusion welding, and that's one of the early examples is people use this friction stir and successfully weld those tanks, and this is one of the longest structure friction stir weld for that kind of applications. Right, so a smaller one I think is 6 or 7 seat small planes, Eclipse. Right, so in the late 1990s, they formed a company and designed a whole manufacturing system to start with friction stir in mind. So let's cut down all the histories. And by 2008, 260 jets delivered, right, but 2009, bankrupt. But that had nothing to do with a friction stir. And 2011, now they start taking order again and back to production. Now, but this sequence is some of those the friction stir developments inside that company. Right, this is some of the example sent to us from TWI, and you can actually see. The other one is that nowadays I think it's quite commonly used now for manufacturing of bullet trains, and taking the lead in the early 90s or 2000s is Hitachi's, and later on now is, of course, the application is pretty global. And even in China late last year when I went to China, is the scales of applying that technology of producing bullet, all sort of a train body is so big, and the technology is so advanced. Now, okay, so aerospace, trains, but actually the first application of friction stir is actually for marine, right? So here are some of the examples, all right? So from in the beginning, a fishing boat, superliner, but also in New Zealand, as I mentioned before, we also have the success of 4 of those naval vessels and built by using friction stir panel, manufacturing in New Zealand. Okay, by the mid-2000, 2004 and 5, and the academic community is start to feel that the application of that technology, so it's been success, idea, development, and application. But among the communities, academic community, we feel that the application of these technologies is well ahead of understanding the friction science and friction stir science. So in various conferences, people call for a deeper understanding in the physics of what's happening. And one of the examples, 2009, and this is a call for a mapping of the process, measurables, and the resulting microstructure and properties. But of course, in AUT, we also want to, right, you map that, but what's happening in between? And that's some of those, Song is not here, Wei Gao and myself, supervisor, PhD student. Song spent a few years trying to figure it out during friction stir what's happening inside there, and he completed his PhD the year before. Right, so to illustrate just a little bit, so you can see over the last many years, it's been a very large amount of research has been done in this work, and there's a lot of major reviews taken place, and as well as some of the special issues of a journal that many papers just devote to the subject of friction stir. I'll try to just illustrate one of the importances of, right, even the strain and strain rate during deformation. What are they? Right, I think to this day is still quite uncertain. Right, so, and I just call for one of the examples. Some years ago, people said, well, according to some sort of modeling, the true strains, effective strain can be higher than 40. Just imagine, higher than 40 means this one, if you pull that, it's almost forever. It's impossible physically. Right, so this is more down to earth. This one is do a very simple calculation. When you do friction stir, you come around there, you stress, and then you compress again. That's what the number is. Right, of course, this is to do with a lot of modelers, and that's what they do. When you do the modeling, and you come up with the streamline, and then you follow that and try to look for those strain and temperature. Well, this is a flow, but also can be thermal as well. But the problem of up to now that a lot of modeling work has completely ignored, because you have a tool, a pin. It's actually a threaded one, but inside the threaded space has been completely ignored because it's difficult to understand the physics behind that. So nobody actually has modeled that much. I think we start to see people now attempting to do that, but this is kind of that kind of calculation. In terms of strain rate, a few years back, you can see all over the place. So it's difficult to understand. What we have done, we've done a very careful experiment and try to capture during friction stir what freeze the material, and according to the material, we'll try to look at the deformation, knowing the velocity, we'll try to work it out the strain and strain rate, right? So that's what it's actually we figured out here, but back inside the stress space, we still don't have much idea. But also in the same time, Song also did a little bit of work. What's inside there, we'll look at the so-called, look at the microstructure, because you can't measure them. It becomes deformation, it becomes everything is so mixed up already. But you actually can use the technique and chase and look at, if you have deformations, grain would flow in a certain direction. Afterwards, you can actually work it out from. Now we have the SEM EBSD. That's what we can do. So they work out the deformation. Look and with that, and give you a certain pattern. It's pole figures, and that's why it's quite important. And he actually tried to look around it, and you look up from the starting the so-called cubic texture to start to see a little bit A texture, and then A textures, and then A texture, and end up, you can see the pattern. Inside the stress space, it's pretty much like that. So what we come up with, you say, well, let's forget about the details of that. If it's random, you get everywhere. The pattern means there's certain deformation direction. With that, it means if it persists, going around, there's not very much deformation has taken place. Well, that's what we thought. We're still doing a lot of things to verify that. So we'll see that what we found before probably still remain true. The strain is about under 4 and the strain rate is under hundreds. Okay, so I want to illustrate to you, just to illustrate the fact that friction stir science is actually quite complex, right? Quite complicated. And much has been understood, but many phenomena are still to be studied and revealed. But friction stir welding, you don't need, well, for some application, you don't need that science. It can be done successfully and quite easily in a quite wide fields of conditions. And this is an illustration. You actually, if you look at carefully, it means it's a very wide field of conditions. You actually can use for normal friction stir welding, right? So, and that's the reason why it's easy to control, even though you don't understand the details, right? So that's why the application is so vast. But I just want to point out, though, right? But for some application, you got to know a lot more, and this is one of those, the so-called hooking. If you're not careful, we do the lab welding, you end up with some hook there. By the time, if you subject the structure to loading, you end up with a huge stress concentration and very easy to crack, right? So this is some of those. We also have done some study, and I present that a few months back when I was in Beijing. And back to Beijing, let's look at, again, on the application in China. As I mentioned before, it's very vast, large scale application, and pretty much a lot of those, of course, is lab joining, and it's really important though. And after the conference or after the talk, there's one of the chief engineer and one of the senior engineer came to talk to me and discuss this topic, and he said, now in the strain body manufacturing, sometimes when they have that kind of problem, their management tell them, if it's a critical loaded location, do not use friction stir. That's very disturbing, you know. But again, because they don't understand the behavior, right? So it's still some of those, the science we really need to understand. Otherwise, the application can be limited in a way. So, okay, so look at the whole process. Behavior is quite complex, not yet fully understood, but in general, the process is quite accommodating and thus controllable. So the process, friction stir-based process, developed and used, right? But the behavior, I think we need to a lot more to understood. Okay, so those are friction stir. Let's look briefly, look at the futures. Look at the future. How do I look at the future? I borrow something for the place I used to work, right, from CSIO. Looking at the future is additive manufacturing, shaping the futures. Right, so what they are talking about here, of course, is traditional machining. Now, if you have those 3D printings layer by layer, coupled with the high energy beams, you can actually make a components. It's very complicated, right? So that's the futures of manufacturing. Okay, let's look at the future of manufacturing. I cite some of the examples. It's very promising. A lot of medical field and aerospace manufacturing. You go to a lot of conference now in the materials conference, you actually have a lot of session now, well, from the materials engineering field. That's on the subjects of additive manufacturing under using high energy beams to produce those device structure properties for medical field, for aerospace manufacturing. Right? So it starts with powder, of course, and it ends up with what? It is, what do we see over there? Well, to a lot of you probably don't mean very much. It is a dendritic structure. It is a typical melt, liquid, and solidify, and in a dendritic way. All right. So if you look at the bar over there, it's a very fine structure. Means very high cooling rate, right? But remember, I mentioned before, solidification, associated phenomena in manufacturing, often need particular attention. I think this technology we also need a lot of study before we actually apply that to a lot of field. We need to understand that. And the good news is now AUT, we are going to get these systems, and I'm sure I will put and do some study on some of the phenomena there, if I'm allowed. All right, back to, wow, that's the future. Back to the past. Right, let's look at one example back to the past before I finish. Right, and let me just look at these examples. This, and it's in a conference in the 90s. That I can't remember, it's 98 or 97, in a materials conference in Australia. It was, a keynote speech was delivered by I think it's one of the CEO in BHP Steel. He gave a graph. Well, this is from my memory. That's what the graph like, right? So you have the profitabilities, start from iron mining, and then iron making, steel making, rolling, and you see a lot of manufacturing. Of course, their profitability is very low, right? So that's in the 90s. And with that, of course, the Newcastle, we used to spend a few years there, is Newcastle's no more as a steel city because of that. And also, 3 years ago, I went to Lehigh University, and I was showing around the city up to one of the mountains. Is Birmingham Steel's lab used to produce a lot of good development works. Zinc is actually originated from that lab. But again, when we look around the city, again, it's no more. You see all the big structure standing there, but no production of steel anymore. So Birmingham no more as a steel city. I think that's quite symbolic, though, in a way that in the 90s or early 2000s, there's a lot of manufacturing in this region, in the US, it starts to shrink and shrink. It's gone somewhere, right? I think we don't have to dispute the fact of that. But let's look at a little bit on the reasons Obama's administration proposal to establish a national network of manufacturing innovation. What it does is try to address that, right? Because of those, I think, right? the decades of a decrease in employments is because of manufacturing. It's gone somewhere. Now they try to establish that. With that, there's two things. Very good, important ingredient. The first one is the National Robotic Initiative, and the other one is Materials Genomes Initiative. What does it mean? There's three components of that. One of those is develop computational tools. The other one is set up vast database available for everybody's use, but also a lot of scientists have to go back to the lab and make sure the behavior can develop a good model so you can use for computational tools, right? So the materials behavior is very important. Why do they do so? Because they realize you can actually in laboratory invent a lot of new materials, good material, but to the final usage, you have to go through a whole manufacturing process. This process, without the understanding of those, it takes normally 15 to 20 years. That's too long, right? So what happens today is I'm trying to probably explain to you a little bit in manufacturing, at least some of the very important manufacturing, the prediction and control of materials behaviors is very, very important. And with that, I hope today I have also linked that behavior manufacturing innovation. And with that, I would like to thank so many people, but I wouldn't put the name down. And to, first of all, my supervisor during my graduate works, Dr. Gregory and Professor Roy Sharpson is not here today, and Dr. Clark is not here today. And I also like to thank a lot of those from Chem and Max and the former staff member, present staff member, technicians, and so on. And also those people I've worked with in Pasmingo, in CSIO, and also colleagues here at AUT. And also those people from, for example, NZTEs, Daryl Wang, and also those from the New Zealand manufacturing companies. And I also want to thank the materials community. Even though we are small, we try to put some emphasis on the importance of materials in New Zealand as well. I thank those colleagues I worked with the last couple of years, and also the member, and also my families, and also the most of all of you here today. Thank you.